Okay, now that we've seen quite a few examples of martingales, the natural question is, if I have a martingale, can I build new ones from old ones? Now, everything in the definition of a martingale is a linear property, so it's pretty clear that if you take linear combinations of martingales, you're still going to have a martingale. But by linear combination, I would mean a sum of martingale's time coefficients, with the coefficients being numbers. Now, we're doing probability here, so everything can potentially be random. So I'd like to have not just standard linear combinations, but maybe random linear combinations where I allow my coefficients themselves to be not just numbers, that is to say deterministic random variables, but actual random variables that vary over the probability space. Now the question is, what sort of conditions would I need to put on the coefficients to guarantee that these random linear combinations of martingales will still remain martingales? That's what we're going to answer right now. And you can tell from the definition that there's going to have to be some limitation in terms of measurability with respect to filtration of what these random coefficients can be. So let's have a look at the first definition that we're going to use here. Is the definition of a predictable family of random variables. So you have a family of random variable, you call it predictable. It's always with respect to filtration. If an is fn minus 1 measurable. So being predictable is something slightly stronger than being adapted. Being adapted would mean that an is fn measurable, but we're asking an to be fn minus 1 measurable, and fn minus 1 is smaller than fn. So this is something harder. And then the next definition, the definition of a Martingale transform is, if you give me a predictable process and a martingale, I can form the Martingale transform of mn by an in the following way. You do a linear combination of the increments of mn, multiplying it by the coefficient aj. Notice in this definition that if I were to take aj constantly equal to 1, then I would have a telescoping sum, and I would get the mn tilde being mn minus m naught, and very often we choose m naught to be 0. So you can recover your standard martingale if you do a Martingale transform and you transform it using the sequence constantly equal to 1. Right, but we're looking at something a lot more general, but we're only going to allow these random coefficients to be not just adapted, but predictable. If they were not adapted, then mn tilde would have no chance whatsoever to be a martingale, because it wouldn't even be an adapted process. Adapted would be enough to make, adapted aj would be enough to make mn tilde adapted. But what we are about to see in the theorem 2.1.1 is that asking for aj to be predictable will guarantee that the Martingale transform is itself a martingale under an additional condition in the process. Now, let's, before we look at the theorem and prove it, let's try to get a better feel for what these definitions are telling us. So predictable means that you can decide on the value of an given information accessible not just at time n, but at time n minus 1. So predictable processes would be used typically to model strategies. So you have information about what happened in the past, so up to time n minus 1, you know at time n you want to make a decision at time n, and you make that decision based on the information you have at your disposal and not based on something that's going to happen in the future. Obviously, that would break down adaptiveness, but also not based on anything happening right now when you're supposed to make the decision. So one applied way to think about this Martingale transform is that you have a martingale representing something like your accumulated wealth, let's say when you play a game. So what we have here is the increment of that accumulated gain, so really your gain between time j minus 1 and j, and this tells you how you should modify your bet So what you should multiply your increment by. So it really from a modeling point of view, if you think of MJ as being our first example, an accumulated wealth of playing a fair game, this tells you how you modify your bet at each point. And we'll see that if you do it in a predictable manner, that is to say, any strategy based on the information you had in the past, plus an extra condition, then you stay a martingale. So the game stays fair and your expected gain is still 0. Okay, now that's the applied point of view. Now from a more analytical point of view, what is this? This is really like a discrete integral, right? When you have an integral, something of the form integral of f of x dx, what do? You do a sum, right? That's the meaning of that big S in integral. It's a limit of a discrete sum because continuous time integral or Riemann integrals are defined as limit. And it's a linear combination of a value of a certain function times the increment of your variable, right? You think of x, or you approximate these integrals by things of the form x plus h minus x, where h is a small step size. So what you have here is an increment of your underlying martingale that plays the role of x, plays the role of your variable in standard calculus, and here is what you're integrating. And indeed, we will find later in the course that Martingale transforms are precisely the building blocks of the Ito integral of that is to say, the integral of stochastic processes in continuous time. Now, I also tell you should think of that as a strategy. When we get to the application in finance, that's exactly what we're going to have. We're going to have the value of a certain financial product expressed as an integral, and when you express it as an integral, you'll find that what you're integrating against is going to be exactly your trading strategy, and these increments will represent the change of price in an underlying stock. So this is where we're going in terms of application. And in terms of analysis, well, we are moving from expression like this, which are finite approximation of integrals, or if you rather integrals of simple functions, and we're going to move from integrals of simple functions to general integrals like we always do in any integration theory. Okay, so on our way to that, we are going to show this theorem 2.1.1, that tells us that if you modify a martingale, you do a Martingale transform using a predictable process, you stay a martingale. That is under one condition. And that condition is that your AN stays bounded. That's the L infinity norms. That is to say, the supremum of AN, let me write it up here, the supremum of AN of omega over all the omegas in your probability space. So if your process, your strategy, your predictable process stays bounded and you're predictable, then the transform of a martingale stays in martingale. So this tells you from an analysis point of view what sort of predictable processes we will be able to integrate. From an applied point of view, that tells you that if you want the fair game to stay a fair game, you need some restriction on what the trading, on what the bets can be, or on what the strategies can be. So let us prove this theorem. What have we got? We've got a filtration of our probability space. We have a martingale with respect to that filtration. I didn't make it precise whether it was an L1 or L2 martingale. If you start with an L1 martingale, you get an L1 martingale. If you start with an L2 martingale, you get an L2 martingale. Let's just say it's an L1 martingale. If it's an L2 martingale, you'll have to prove a little bit more to show that the transform is also L2. But that's not particularly relevant here. So I start with an L1 martingale with respect to Fn. And I have a predictable process AN also with respect to the given filtration. Now I've defined the transform as the linear combination of aj times the increment mj minus 1, and I want to show it's a martingale, so I need to show that mn tilde is fn measurable. I need to show it's still in L1, and then I need to show the property using conditional expectation. So the measurability to start with, well, mj is fj measurable for all j equal 0 to n, and fj is included in fn, so being fn measurable is easier, so it is just fn measurable for all j equals 0 to n. Now that's true for mj, that's true for mj minus 1, of course, and so the last bit is aj. aj is, well, it's even better than fj measurable, it's fj minus 1 measurable, and therefore it's fn measurable for all j equal 1 to n. So now I have a finite combination of sums and products of fn measurable variable. I am myself, me being mn tilde, fn measurable. Cool. So that's the measurability property. I should have fixed my n to start with. Now I need to see that it's in L1. What can I say about the L1 norm of mn tilde? Well, it's a finite sum. I can use triangle inequality and just control that by the sum of the L1 norms. That's the triangle inequality for the L1 norm. Now aj is in L infinity. It's bounded, so the integral of a product is always smaller than the sup norm of one element of the product and the L1 norm of the other. So this is a very simple version of Euler inequalities, if you've heard about those, right? But it's just a consequence of the fact that the integral of f omega g omega dp omega is certainly smaller. You can control f by its supremum, and then the supremum doesn't depend on omega, so it's controlled by the supremum of all omegas of f of omega times the integral of g omega dp omega. That's what I'm using here. Okay, and that's where the assumption that my AJs were not just in L1 or L2 but actually in infinity comes to be helpful. So this is controlled by the maximum, this is a finite sum, so maximum j equal 1 to n of the sup norm of the AJs times 2, let's say, times the sum j equal 1 to n of the L1 norms of j equals 0 to n of the L1 norm of the MJs, and those are finite because all of my MJs are in L1. So what have we got? We've got that mn tilde is in L1 omega fmp. In particular, it makes sense to take conditional expectation of that mn tilde, and it's and it forms an adapted process. Now the last thing I have to do is check the conditional expectation property, the defining property of being a martingale. So I need to compute the conditional expectation of mn tilde plus 1 given fn and show that this is mn tilde. Now what is this? I'm actually going to subtract from that mn tilde and show that this is 0. And note that because mn tilde is mn measurable, this is exactly the same thing as the conditional expectation of mn tilde plus 1 minus mn tilde given fn. That's using the fn measurability of mn tilde and the take out what is known property and the fact that the conditional expectation of 1 is 1. Right. Nice little exercise if you haven't understood that fact quite yet. We've used it actually in other places. So what is the difference between these two things? Well, m tilde is given by a sum, so the difference between the two is exactly the an plus 1 times m of n plus 1 minus mn given fn. Now I'm going to use again the take out what is known property, but using the fact that an plus 1 is in L infinity omega fn, because an, the process an is predictable, so an plus 1 is not just fn plus 1 measurable, it's fn measurable, so I can take it out of this conditional expectation and I get an plus 1 times the conditional expectation of mn plus 1 minus mn given fn, but this has to be 0 because mn is a martingale. So we've seen that one can modify a martingale using a predictable process, and as long as this process is bounded, we still have a martingale. We now going to focus on a special case of this sort of transformation, which is called stopping a martingale using a stopping time. So from an applied point of view, it's a special kind of strategy where you decide to stop at a certain point of time, but this point of time is itself random. That depends on random event happening. This is going to be very important in everything we do after, and this is going to correspond from an analysis point of view to the fact that we want to be able to integrate appropriate simple functions, but simple functions in the context of stochastic analysis are not going to be linear combination of characteristic function with the coefficients being numbered. They're going to be linear combination with the coefficient being random variables themselves, because everything can be random in what we are looking at. So we need to find out what would be appropriate from that perspective as an integrand to an integral, if you want to think in an analytic term, or what sort of random variables can we use to determine an exit strategy in a fair game, for instance, or in the trading scenario that we're going to be looking at in the financial applications. So what is a stopping time? It's extremely important probability concept. It is a random variable with value in whatever you use to represent time, which in this part of the course is just the natural numbers, but we allow also tau to take the value infinity if something never stops. Now, a stopping time is defined with respect to a filtration. So a random variable with value in the set that you use for time is a stopping time with respect to a given filtration if the set of those omega such that tau of omega is smaller or equal to n is fn measurable. Now and that has to be for each n, of course. Now what is that saying? It's really saying that if tau describes when you should stop, the question whether or not you should stop by time n should be decidable based on the information you have at time n, right? For it to be an exit strategy, it has to be something that you can decide without relying on information about the future. And that is expressed exactly in that way. The set where tau is smaller or equal to n has to be fn, has to be a set in fn. Okay. So based on this notion, we're going to introduce what we call a stop martingale. So what we call a stop martingale is give yourself a martingale, give yourself a stopping time, everything is with respect to a given filtration, and you look at the process mn minimum tau. And what does mn minimum tau mean? Let me give you the definition here. Mn minimum tau, well, it's a random variable. So at a point omega in my probability space, it returns the value m minimum of n tau of omega. So the time itself, is not something random, and you're using the martingale at the time where you stop. So depending on omega, that time might be before or after n. So you take the minimum of n and tau of omega. Right, so that's what's called a stop martingale, and we're about to see in the proof that a stop martingale is actually just a special kind of Martingale transform of the martingale you start from. You just have to choose the predictable process to transform it appropriately based on tau, and then the theorem 2.1.2 will be a consequence of the theorem 2.1.1 that we saw before. But it's an extremely helpful consequence, as we will see in applications right after that. So let's prove theorem 2.1.2. I have a filtration to start with. I have a martingale with respect to that filtration. And I have a stopping time with respect to that filtration. Okay, and I form the stopped martingale mn minimum tau, which is the map that sends omega to m at time minimum of n and tau of omega applied at the point omega. And I want to show that this is still a martingale. So I'm going to do that by showing that mn minimum tau is actually a transform martingale of mn for an appropriate predictable process. So here's the process I'm about to define, what I'm going to use for this purpose. So define an to be the indicator function of the set where tau is greater or equal to n. Right? That is to say the map that sends omega to 1 if tau of omega is smaller or equal, is greater or equal to n, and 0 if tau of omega is strictly smaller than n. And tau of omega being strictly smaller than n, because n is a natural number, is really the same as saying that tau of omega is smaller or equal to n minus 1. Okay, so let's do the Martingale transform of mn adapted to the sequence aj with respect to the sequence aj. Right, so this is a Martingale transform. Is that a martingale? Well, notice that first of all, an is predictable. Now, why is an predictable? An is 1 when tau of n is greater or equal to n, and 0 if tau is smaller or equal to n minus 1. So an is really at a point omega, say, equal to 1 minus the characteristic function of tau being smaller or equal to n minus 1, indicator function of that at omega. So it's a constant minus the indicator function of a set which is n minus 1, fn minus 1, which is in fn minus 1. So this indicator function is fn minus 1 measurable. So this is fn minus 1 measurable since tau is a stopping time. Therefore, an is predictable. Okay. So we have a predictable process. Is it bounded? Well, of course, it's an indicator function. It only takes the value 1 or the value 0. So this is 1 for all n. So we have that mn tilde is a martingale by theorem 2.1.1. Now we're going to show that mn tilde is equal to mn minimum tau for all n. And that would conclude our proof. So how do we do that? Well, we're going to look at two possible cases. First of all, what happens when tau is greater than n? Well, when tau is greater than n, I'm summing indicator function of tau greater than j, that's what aj is, time mj minus 1. But what happens in this case? Well, this information is redundant. If tau is already greater than n, then it certainly is greater than j. So in that context, I'm really summing from j equal 1 to n mj minus 1. I know that my aj is constantly equal to 1 on the set of omegas where tau of omega is greater or equal to n. And then that's a telescoping sum, and what I get is the integral tau greater than n of mn minus m naught. And I should have defined from the start m naught to be 0. That's the way we initialize our martingale in the theorem. Okay, so, but what is mn? If n is smaller than tau, then n is the minimum of 1 and tau. So this is equal to, on the set where tau is greater or equal to n, mn minimum tau. Very good. Now what about the other set when tau is smaller than n, which is the same as saying that tau is smaller or equal than n minus 1. Okay, now in this case, tau is some number between 0 and n minus 1. And this indicator function times that indicator function is going to be 0 when j is above tau of omega. So what we have here really is a sum. So on this set where tau is smaller than n minus 1, we have a sum from j equal 1 to tau of omega of mj minus 1. And again, these telescopes, and you get the indicator function of tau being smaller or equal than n minus 1 times m of tau of omega. I should have fixed an omega in here. If not, my notations are not valid. Well, they are abuse of notation, which I'd rather avoid at this stage. Minus m naught, which we're going to set to be equal to 0. So what we're getting is whenever tau is smaller than n minus 1, we get m of tau of omega at point omega. And this is exactly on the set where tau is smaller than n minus 1, m of n minimum tau of omega. Okay, so what have we shown? We've shown that either in this set or on this complement, mn tilde is equal to mn minimum tau for all n. Because we had proven that mn tilde was a martingale, and the stop martingale mn minimum tau is a martingale itself. That concludes the proof of this second theorem. Now we're going to see how helpful it is in applications.